Welcome back everyone. In this lecture I am going to explain you how to actually build any 5-dimensional representations from its irreducible sub-representations. So I am not going to give you much details, but I am going to roughly say what is going in the general theory of representations. So let us recall what we have done before. So we actually proved an important result that says any 5-dimensional representation has a filtration such that the successive quotients are irreducible. So let me just write down the statement. So let us take V to be 5-dimensional representation of capital A. So then there exists a filtration. So we are calling it as V0, V1, etc. Vk, which is the full space, such that so when we take the successive quotients Vi modulo Vi minus 1, they are all irreducible. So this is actually just follows from the induction. So now let us actually focus on the length of the filtration. So if we just assume that all these spaces are actually proper in the successors, so then based on that we will be able to actually define the length of the filtration. So we can very well just assume that so these are all proper subspaces in its successor. So now this k, one can call it as a length of the filtration. So now if the length is just 2, then let us see what happens. If length is just 2, then we will have a scenario like this. So we have V0 which is sitting inside V1 and then which is sitting inside V2, which is the full space. So now note that so you have V1 which is irreducible, which is sitting inside this V, and then when we take this V2 modulo V1, which is V modulo V1. So these two extreme things are actually irreducible. So this one is irreducible and this one is irreducible. So this is what happens when k equal to 2, that means the length to filtration. So now this means that whatever that is there in the middle of this modules, that is capital V. So that is in a way built from these two irreducible representations. So one is indeed sub representation, the another one is quotient representation. So you can see that V, so we do not know how V is built, but it is very clear that because V1 is a sub representation and then we have a quotient V modulo V1, that is another irreducible representation. So V is indeed built from V1 and V modulo V1, but it could be very complicated way. So it does not need to be somewhat very trivial way, in a somewhat complicated way. So what we mean by that, like so basically like we have started with two irreducible representations, let us say V1 and so maybe let us call it U or W to use different notations. So we just start with two representations, let us say U and W. So both are irreducible. So both are irreducible. So, then what we are interested in? We are interested in actually making a new representation, we call it capital V, from these two representations. So, satisfying the property that, for example, this U becomes indeed sub representation of V, and then this W becomes quotient of this V. Okay. So, in that sense you can see that V is indeed actually made from these given irreducible representation U and W, and these representations that actually fit in the middle, they are called extensions of this W by extensions of this U by W. So, these are called extensions. So, we already know one possible extension of any two given representations. We can, for example, so one example is that one can take U direct sum W for an extension. So, this is called trivial extension. Okay, but whatever that is actually fit into the middle, it may not be actually just obtained as a direct sum of U and W. It could be in a much more complicated way. So, in order to understand that, let us try to understand what happens when we actually use the action of elements of this capital A. So, let us say actually this U is given by a map rho. So, the action of capital A is given by rho. So, this U comes with rho, and then this W comes with xi. So, these are all the given representations, let us say. So, now what are we looking at? So, we are looking at some representation that is built from U and W. So, when we say it is built from U and W, that means as a vector space it is merely a direct sum of U and W. So, that is what we expect. Okay. So, this is a direct sum of representations, direct sum of representations. So, if we are actually going to cook up something for V, space for the V, the natural space will be just a direct sum of vector spaces of U and W. So, basically that is simply the vector space extension. So, that we know for example how to get. So, we can actually treat U as, for example, subspace of V, and then we can simply take a complement of U inside V. Okay. So, that is how the W can be obtained as quotient of V by U. So, now if we think about it, if we are actually interested in defining an action of capital A on capital V. Okay. So, for that what we do, we just simply take an element. So, let us take an element capital A fix an element A in capital A, and so we have action of rho A on U, and then we have the action xi A on W. So, because rho is the representation given from A to the endomorphism of U, and xi is the representation that is given from A to endomorphism of W. So, now somehow we want to construct this rho tilde. Okay. So, that is indeed a representation of V, which as a vector space, we want it to be U direct sum W. Okay. So, what happens if we actually have this rho tilde? So, then the rho tilde of A, so it is going to be a map from V to V. Okay. So, V is nothing but U direct sum W, and u direct sum w as vector spaces. So then the property of this rho tilde will be, so you take this rho tilde of A restrict to U, so that is supposed to be exactly equal to rho of A. So this is the first property. The second property is that when you actually look at the quotient, so this U becomes invariant for this rho tilde of A. So then we can actually have this induced map. So maybe let me just write it as rho tilde of A defined on V modulo U. So which is a map from V modulo U to V modulo U, which is exactly identified with the W. So then we expect that this map is exactly equal to xi. So this is our xi of A. So this is what our expectation. So this is our expectation. So if we rewrite this in terms of the basis of U and W, so putting them together, so let us call it B1 is basis of U and B2 is basis of W. So then B1 disjoint union B2 becomes basis of capital V. Then if we talk in terms of the basis, then we can easily see that the rho tilde of A, the matrix of this with respect to B1 union B2. So that is going to be exactly in this block form, because rho tilde restricted to U is just rho of A. So that means it is a map from U to U. So this is a map from U to U. So that means it is going to be just the block matrix corresponding to rho of A with respect to the basis B1. And then whatever we have here, it is going to be 0, because U is rho A invariant. And now when we are actually looking at this rho tilde of A induced map on V modulo U, that we expect it to be xi of A. So that means modulo U, we will have here xi of A with respect to the basis B2. But this part which is supposed to be filled, so that is going to be some entries with respect to A, and that is going to be a, let us say, some map. Okay, this can be realized as map. Let us call it f of A. So where this f of A indeed defined, so you can easily see that. So this f is indeed a map from this V mod U, which is W to U. So this f of A, it actually defines a map from W to U. So why is that? Because we are looking at so the way, so if you recall the way we actually write down the matrices, you can see that so we have started with the basis of B1. So let us list it as some U1 etc. UK, and then list this basis B2 as some W1 etc. WM. So then if you take this rho tilde of A applied on UI, so that is going to be some linear combination of UJs. So it is going to be some, so let us say this is UJ and then this is BIJ UI, where I ranging from 1 to K. All rest of the entries is going to be 0 for WIs. So that is why you are getting this part of the matrix. But for the second part of the matrix, so rho tilde of A applied on some WR, so this is going to be equal to, again you get some scalar linear combinations of ui with some entries, let us say CIR, and then plus again you get some scalar entries with respect to wi. So, let us call it DIR. So, then these entries are going to give you entries for this block, because when we actually go modulo this u, so then so this is going to imply that rho tilde of a WR modulo u is going to be exactly equal to summation DIR WI plus u. So, that is the reason that we get this part for xi, but there is this part which actually contributed from this part. So, that is actually kind of defines this f of a. You can see that. So, let me just rewrite. So, this f of a on this wi. So, recall that. So, I have used WR. So, this is the part I am writing. So, so this WR f of a WR is going to be exactly equal to this u part of the sum, which is summation CIR ui. I range from 1 to k. So, this is how this f of a defined. So, that means f of a is a map from W to U. So, f of a live inside map from W to U, and it is easy to see that because it is all everything is linear here. So, this lives inside the home W comma U. So, basically you are getting a map f of a. So, that is indeed map inside home W. So, rho tilde of a is indeed given by these blocks, where the left topmost is rho of a, and then this is 0 and this is f of a, and then this is exactly xi of a. So, this is how the matrix representation of rho tilde of a actually looks like. So, in terms of the maps, you can see that you have these linear maps sitting here. So, we already know that rho of a goes to rho of a and xi a goes to xi of a, both are actually gives you algebra homomorphisms. So, that is how we started with, but this a goes to f of a, what kind of map it is. So, all we know is it is actually linear map. So, that is something one can easily check, because everything we are doing is linear. But then one can ask whether so when is actually this map a goes to f of a is going to give us indeed representation. Okay. So, the question is determine the necessary and sufficient conditions. So, determine the necessary and sufficient conditions for which conditions on f of a, so that rho tilde becomes a representation. Okay. So, the answer to this question, it is not that difficult to actually determine what will be the condition. So, the answer is indeed. So, I am not actually going to get into the details of this. So, this is just for the motivation part. So, basically f is supposed to be one cocycle. So, this is where actually bit of homological algebra gets into representation theory. So, when these maps A goes to f of A are one co-cycles, then we can make sure that rho tilde of A is indeed defines a representation. So, basically this condition actually that tells you that. So, when we start with two representation u and w, and then if we take this capital V, which is actually sitting in between u and w, so which is actually as a vector space formed as a direct sum of u and w, and we will be able to lift the action of u and w on V when this f is actually which is comes under the picture becomes one co-cycle. And of course, we will be interested in representations that are actually fit into this diagram that so in diagram language, so we write this u is injectively sitting inside capital V and w becomes the quotient of V, that means V surjects on W, and we are looking for the representation that actually fit into this diagram, and these representations V are called extensions of W by U. And now in order to obtain these extensions, as I said, we need to actually find out when this f actually satisfies some conditions called one co-cycles. Under that conditions, we will be able to actually say that this we will be able to define this extension V, but of course, we will be interested in inequivalent representations. Then in terms of actually these co-cycles, so what we can say, so whenever they actually differ by co-boundaries, so which are called one co-boundaries, so then we will be able to say that the extensions that we have defined, so they will be indeed isomorphic. So basically this V is nothing but, so let us put it in the language of direct sum. So this V, let us call it, it is comes from U direct sum W with this one co-cycle F. So now given two one co-cycles F and F dash, and if they actually differ by one co-boundary, if F minus F dash is one co-boundary, so then we will be able to say that this U direct sum W defined using F will be isomorphic to it is U direct sum W defined by F dash. So these two representations will be isomorphic. So that will actually implies that this x to 1, which are the inequivalent extension that you get it from W by U. So these indeed will be isomorphic to one co-cycles modulo one co-boundaries. So I am not getting to the detail what is one co-cycle, what is one co-boundary and all, but homological algebra actually allows us to actually determine very explicitly what are all the inequivalent extensions that are possible that fit into this diagram. Okay, so that actually indeed tells you that, so we will be able to actually talk about extensions of these irreducible representations. So filtration indeed guarantees that any given finite dimensional representation that is actually built from taking extensions of these irreducible representations. So if we have this filtration, so let us go through the filtration. Maybe we can do length 3 case. So if we start with the filtration, so let us say 0, which is V0, contained in V1, contained in V2, contained in V3, which is the full. So then we know that V1 is irreducible, and then V2 modulo V1, so that is irreducible, and then V3 modulo V2, so that is also irreducible. So all these successive quotients, they are all irreducible. So now you can see that V2 is obtained by taking V1 as subrepresentation and then V2 modulo V1 as quotient. So this way, if we know these two representation V1 and V2 modulo V1, then we will be able to build V2 out of these two representation as an extension. So now we are interested in the original representation V3. How do we get V3? Now V2 is already built. Now V2 sits inside V3, and then we have this quotient V3 modulo V2, and this is indeed irreducible. So this is irreducible, and we already built this already. Let us say we built V2, V2 is built. So now V3 is just built from these two already known representations, that is V2 and V3 modulo V2. So this basically tells us that if we know all the irreducibles and then how to build other representations from irreducibles, then we will be able to inductively build all representations, 5 dimensional representations of capital A. So this is how actually kind of irreducible representations become building blocks for 5 dimensional representations. But even though they become building blocks, but it is actually very challenging problem to determine what will be the extensions of given irreducible representations. So this actually poses the following questions. So first of all, one wants to classify all the irreducible representations. So classify all irreducible representations. The second question is how to build extensions. Okay, so the determine extensions of irreducible representation. So this is how we will be able to actually build all representations. So to start building all representation, first we need to answer these two fundamental questions. But of course, when we are actually doing representation theory of finite groups, we will see that finite group representation theory becomes somewhat simpler. So because the category of finite dimensional representations of finite groups, that is indeed semi simple. That means any finite dimensional representation will be written as direct sum of irreducible representations. So in particularly all the extensions, they all become trivial extensions. So we will not have any non-trivial extensions between irreducible representation. So that actually kind of simplifies the second problem. And again classification also again we will be able to do in some of the finite groups. Okay, so let me actually quickly tell like so what happens in the broad picture. So we have these irreducible representations which are we have seen building blocks of any finite dimensional representation, and they are all indecomposables. So our first observation said that any finite dimensional representation can be written as direct sum of indecomposables. So that means so we have these completely reducible representations which are direct sum of irreducibles. so which lie inside all finite dimensional representations, which are actually direct sum of indecomposables. So mostly like in general representation theory, this gap could be actually very large, like not all finite dimensional representation need to be completely reducible. So that is where like the representation theory indeed becomes much more interesting. But here in this particular situation, when we deal with finite group representation theory, we will see that this gap is not there. So that actually indeed makes somewhat our life easier. So in general representation theory, you want to actually classify all possible indecomposable representation. So we have already seen one example where determining just indecomposable representations of this one variable polynomial algebra is equivalent to proving Jordan canonical form existence and so on. So but you can also see that even in that very special case, so it is not that easy to prove or classify all the indecomposables. So this is actually a very hard task, but sometimes in some categories or for some algebras, it will be easier to determine all possible irreducibles, but sometimes the gap could be really this gap could be very large, but that will make our life difficult. But anyway, that is how like the space of representations becomes interesting. Okay, I will stop here. So we will actually this is all I wanted to say about general theory of representations. So from next class onwards, we will stick with finite group representations, and then we will actually explore what happens to that category of finite dimensional representations of finite groups. Okay, I will stop here. Thank you.